I want to welcome Paul Vinik, Vice President of Cathodic Protection with GPI, and he's going to discuss the success of two 30-year-old cathodic protection systems.
Good afternoon, everybody. Thank you for coming. I'm Paul Vinik. It's a privilege to be here, and it's my privilege to discuss the success of two 30-year-old cathodic protection systems. So where are they? The Crescent Beach Bascule is just south of Jacksonville. It traverses the intercoastal waterway and is within a few hundred yards of the Atlantic Ocean. Howard Franklin traverses Tampa Bay, which is an estuary of the Gulf of Mexico. Florida has 1,350 miles of coastline, more than any other state except Alaska. And so you can see where the two bridges are located. These two cathodic protection systems are in service. The first protects a double-leaf bascule, and the second a major interstate highway. See the pictures of the two structures. First of all, the Crescent Beach is State Route 206 over the intercoastal waterway. It's about a half-mile long, one lane each direction, about 12,000 AADT, and about 7% of that trucks. It opened to traffic in 1975. Howard Franklin is, again, in Tampa. It's Interstate 275 over Old Tampa Bay. It's a fixed bridge, about 3 miles long, 4 lanes each direction. That is correct. It's about 178,000 AADT and about 5% trucks. It opened to traffic in 1960. So there are 5 focal points that I want to discuss today. First, the technology and science. How does CP work? That includes potentials and their meaning, corrosion cell and CP circuitry, design, how do we implement CP, the construction, taking us from the drawings to the real life, and the maintenance and economics involved. First of all, potentials and their meaning. Everything that can be observed has a native voltage that can be measured. A potential is the difference in voltage between two objects and is the driving force in a corrosion cell. Reference electrodes provide baseline and are used to quantify potentials for corrosion measurements. So what we've got a reference cell placed on a concrete substrate with a digital voltmeter connected to the steel. We've got a wet sponge to provide to reduce resistance between the reference electrode and the concrete. We've got the steel reinforcement in here. We've got the positive hooked directly to the rebar. So ASTM C876 tells us that the standard test method for corrosion potentials of uncoated reinforcing steel and concrete, and it provides the probability table that I've put in this slide based on those potential measurements between the steel reinforcement and the concrete. Energy flows downhill, right? It'll flow from high energy materials to low energy materials. This is the fundamental principle in corrosion and is also the second law of thermodynamics. This is illustrated using the very common zinc anode connected electrically with steel. Unconnected electrically, both the zinc and steel samples will release electrons to the environment, and both will corrode. However, if they're wired together, the higher energy zinc anode will pass electrons, which is a current flow that can be measured in amps, to the steel. When electrons flow from a metal, the metal oxidizes and corrodes. In this scenario, electrons are flowing to the steel rather than from it, preventing corrosion. Taking advantage of the higher energy zinc alloy and the second law of thermodynamics to protect the steel from corrosion. This is an example of a galvanic cathodic protection circuit. An impressed cathodic protection circuit utilizes the same basic principles, except the flow of electrons is provided by a DC power source rather than a higher energy metal alloy. I wanted to show also that a cathodic protection system can be modeled using an electrical circuit with capacitors and resistors. So how do we apply this technology in bridge components? Let's start with a galvanic pile jacket system, which mitigates corrosion in the tidal zone. The most severe corrosion occurs in the tidal zone, where there's an abundant amount of oxygen and continual wet and dry cycles. We wire the steel reinforcement to a zinc anode. Here's our anode in the schematic. Below the waterline, we install bulk zinc anodes by embedding a reference electrode in the grout and wiring the components into a junction box that's accessible. We monitor the performance of the system by measuring the potential between the grout and the steel reinforcement. While the materials differ, these same principles are applied to pier caps and bridge decks. So now let's go back to our case study. First, let's look at the Crescent Beach Bridge. It opened to traffic in 1975, and you can see by the pictures, by 1986, The use of low-density concrete, not enough cover, and just overall poor construction resulted in significant corrosion and spalling after only 11 years. FDOT rehabilitated these elements by removing the bad concrete, installing additional reinforcement, installing a CP system, and then encasing it with new concrete. Here's a picture right out of the design, out of the plans for the project, showing a pier cap. Here's what the repair looked like in real life. The Crescent Beach pier caps received an impressed current system. The existing concrete was repaired. A titanium mesh anode was installed, along with additional reinforcement to restore structural integrity. The pier footing pictured still needs to be formed, but is almost ready for placement of the new concrete. You can see the shadow of the titanium mesh in here. So the picture now on the left is of an off-the-shelf pile jacket fitted by the manufacturer with spacers, and the spacers create an annular space for the grout, a zinc anode expanded mesh, wire mesh, and it is pre-wired for easy connection to a junction box for monitoring. Once the jacket's installed, it's fully filled with cementitious grout. The picture on the right is of an installed jacket that, once the wiring's finished, will be complete. The bottom of the jacket should remain submerged. The top of the jacket should be approximately 6 foot above the elevation of high tide. So we've got the inside of the pile jacket, we've got a bulk zinc anode, and just a picture of a almost complete pile jacket here system. We've got the wires up here coming out, still need to be finished up and connected. So let's look at some more rehab work. Here's a picture on the left showing a completed pile jacket and bent cap cathodic protection system. The picture on the right depicts channel excavated in the bent cap for the installation of titanium ribbon anodes. You can see on the picture on the left that the ribbon anodes have already been installed. Some more pictures here of Crescent Beach, construction pictures that show the struts and columns that are being prepared for impressed current systems. On the left, concrete repairs are complete. The titanium mesh anode has been placed and is being held with Christmas tree fasteners. The L-bars have been doweled into the existing concrete. On the right, the titanium mesh anode is in place. GFRP L-bars are in place and tied to newly placed reinforcement. So what was the total extent of repairs at Crescent Beach? I showed some pictures how awful it looked in 1986. What all was done? 45 galvanic pile jackets were done, 14 impressed current CP systems on bent caps, 4 piers, including impressed current CP systems on columns, footings, and struts, and the impressed current CP systems have embedded reference electrodes and cellular telemetry for remote monitoring. So, all that's great, but what did it cost, right? Money drives every industry. Here's the money. In 1988, the impressed current titanium mesh anode structural encapsulation CP with remote monitoring. You can see the unit costs there were about $15 a square foot for a total cost of $46,000 in 1988 money. 2017, FDOT did more concrete repairs, some spot painting and installed CP on 21 piles to the cost of about $500,000. 2018, cathodic protection and integral pile jackets, non-structural project was let for about $3.3 million. That's the entire life cycle of the cathodic protection system. FDOT has invested about $4 million in the CP system that have kept that bridge functional since 1986. So now let's look at the Howard Franklin. The pictures depict the condition of the substructure in 1988 after only 23 years of service. Just like Crescent Beach, construction with low durability concrete, not enough cover, and exposure to a highly corrosive environment led to significant early life corrosion and substructure degradation. FDOT chose cathodic protection preservation rather than demolition and replacement. The Howard Franklin is in full load service today. I'm not going to go through the design and construction. It's very similar to what happened at Crescent Beach, and so not necessary to go through it again. This is actually a screenshot from the website that FDOT uses to monitor these CP systems. The installation of the CP systems began in the early 90s on the Howard Franklin. Additional repairs and systems have been installed over the decades. The on and off potentials can be compared for each channel, and the output voltage and current from each rectifier is provided in the data from the screenshot. The data is available online along with the weather conditions. FDOT has some bridges fitted with things like depth gauges and scour to monitor scour and flooding conditions, as well as laser sensors to detect movement. And all of these things can be set up with telemetry. If you look closely at the screenshot, you can see plus and minus voltages here, and you'll see channels 72, 73, all the way up to 92. So there are 92 different CP channels on this, and I don't even know if that's all of them. That's just the screenshot I chose. My point is that there's a lot of CP going on this bridge. It's a large structure that was in poor shape. It's been rehabilitated, utilizing these techniques and doing pretty well today. So now let's again look at the cost of the repairs and the maintenance, because that's really what, we can preserve these bridges, but it has to be cost effective. So this and the next slide contain the contract values let to repair the Howard Franklin from the late 1980s until present day. So I'm not going to go through, each row of this table. There's 3 pages of it. But I do want to kind of hit the bigger numbers. You can see in 1992, there was metallizing performed at about 126,000 square feet of concrete at $12 a square foot for a total value of about $1.5 million. 1992, sacrificial zinc sheet, bulk zinc anodes, etc. About 2,000 square feet of concrete was protected at $42 a square foot, and so on. So we've got more work in 2004, 2006, 2009, another $1 million in 2009, $2 million in 2011 on structural jackets, non-structural jackets, and metallizing. So now let's put the dollars in this discussion to use. There's no user costs, no traffic control costs, nothing like that in the calculation you see on the screen. This is just a simple calculation that makes a lot of common sense to me. By utilizing cathodic protection, FDOT was able to extend the service life of the old Howard Franklin Bridge by 34 years. You're just doing the math from the early 80s. If the new structure makes it 75 years without any additional repair costs, it will have cost the taxpayers of Florida about $10 million a year. At today's cost of $10 million a year, the CP systems on the existing bridge save the taxpayers about $340 million. This is based, this calculation, looking at the slide, FDOT just let a new contract to construct the new Howard Franklin Bridge at $814 million. I rounded that down to $750 to just make my math nice and easy, make things straightforward. That's where the $10 million a year comes from. 2024 minus 1990, that's the $10 million a year. So from 1988 through 2016, a total of 21 contracts were let to repair substructure components of the Howard Franklin, summing to a value of $15 million. Several of the contracts included in this estimate are known to also include repairs to other bridges in the district. But for these contracts, we were not able to separate the investments. And for this reason, the estimated total cost of $15 million is knowingly higher than reality. The picture below shows they're driving piles for the new bridge today, probably, unless they've stopped construction. I cannot say strictly that CP saved $325 million. The calculation shown, though, is representative and provides a perspective when comparing the cost of properly performed preservation with the cost of new construction. I'd like to share 2 excerpts from research conducted into the use of cathodic protection to protect bridges. NCHRP Synthesis 398 on the left concludes that state highway agencies have experienced a reduction in the frequency and cost of bridge maintenance and an increase in service life. Federal Highway publication on the right concludes that cathodic protection is the only rehabilitation technique that's been proven to stop corrosion. Here are the historical inspection reports for the Howard Franklin. You can see that May of 1991, the substructure was rated poor, and based on improvements and preservation, the substructure rating improved to fair and has stayed there until present day. Crescent Beach inspection reports also, and sufficiency ratings. I thought you guys might be curious. The substructure repairs have maintained the condition of both of these bridges and kept them both in full service for over 30 years. There's the most relevant training that I know of available is the corrosion and protection of concrete structures, and it's a 3-day course offered by AMP. If you're interested, I'll be glad to share some information. And with that, if you don't do proper preservation, your bridge will close. And if you have any questions, I'd be glad to try to answer them.
Paul, thanks for that presentation. I noticed that on the Howard Franklin Bridge, you didn't go into all the details, but there was a line item where you talked about sprayed on zinc anodes. Yeah, sacrificial zinc sprayed on select pile caps. Did you have to clean the pile cap before you did that, and was that just sprayed on and just left open to the air, or then you put a concrete overcoat over that?
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.